Hello students, today we are going to discuss about the shear force and bending moment diagram. In the previous videos we have discussed how to draw the shear force and bending moment diagram of a beam subjected to simply supported beam, point load, UVL, UDL and the couple and different types of load. Now in this video we are going to discuss about the what is the relation between the shear force, bending moment and the given loading. So that relation today we are going to discuss. So let us see how to derive the relation. So let us consider a beam. Only some portion of a beam is considered, left portion of the beam is considered. It is supported or support at A, and it is subjected to the UDL of magnitude W per meter. Now I have taken a section 1 at a distance of x from the left support, and another section 2 is taken at a distance of delta x from section xx, section 1. Let us see the enlarged view of this section. While you are plotting the free body diagram of this section, now what are the forces acting on this left part of the section and what are the forces acting on the right part of the section, that we are going to discuss. Now this is the free body diagram of this section, first section between 1 and 2. So enlarged view of this section. Now see here we have considered a section 1 and section 2. Let us consider the width of this section as a delta x. So what are the forces acting on this left part of the section? One is a shear force vertically upward and one bending moment is acting clockwise direction. Then over this section or the beam, a UDL is acting of magnitude W per meter over a distance of delta x, and on the section 2, a shear force is acting S plus delta S and the bending moment in a anti-clockwise direction M plus delta M. So delta S and delta M be the change in shear force and the change in bending moment over a distance of delta x. That is the free body diagram of this one. Then you apply the conditions of equilibrium to this free body diagram of the section 1 and 2. And what are the forces acting? One is the upward shear force S acting at section 1, bending moment M at section 1, then downward force moments. Now you apply the sigma Fy is equal to 0. Here sigma Fx is not applied because the forces are not acting along the x direction, all the forces are acting in the vertical plane. That's why sigma Fy is applied. So by applying sigma Fy is equal to 0, upward forces are taken as a positive, downward forces are taken as a negative, or vice versa. Upward is taken as a positive, downward forces are taken as a negative. So here in this case upward is taken as a positive, downward is taken as a negative. So minus S upward plus W into delta x downward plus S plus delta S downward is taken. This shear force and this shear force we have considered and this load. Okay, by solving this equation, S plus W into delta x plus S plus delta S is equal to 0. Now minus S plus S get cancelled and remaining is W into delta x plus delta S is equal to 0. So finally we will get the relation delta S divided by delta x is equal to minus W. This means that as delta x tends to 0, the above equation becomes ds by dx is equal to minus W. That is the meaning of rate of change of shear force with respect to distance equal to the rate of loading. So negative indicate that vertically downward. Then similarly you take the moment. Again I have shown here the free body diagram of this part of the beam which is in between section 1 1 and section 2 2. So taking moment about the section 1 1, so which forces will create a moment here? Yes, S is not creating any bending moment because S is acting on a section 1 1, so its perpendicular distance from section 1 1 is 0. So who will create a bending moment? This W, this moment, this S plus delta S, and this M. Okay, so taking moment about section 1 1, M plus delta M plus delta M, anti-clockwise positive, minus M, it is clockwise, that's why it is taken as a minus M, minus S plus delta S, it will create a moment in a clockwise direction, S plus delta S into dx, this equation. And last one is a W into delta X into delta X divided by 2. So bending moment created by this UDL. Okay. Then by solving this bracket and neglecting the product of small quantity, we will get the final equation M plus delta M minus M plus S plus delta X is equal to 0. Here plus M and minus M get cancelled, and remaining equation is delta M by delta X is equal to S. As delta X tends to 0, then the above equation become, that is dm by dx is equal to S. So rate of change of bending moment with respect to distance gives the shear force at that instant or at that section. This is a very important relation and it is used when a shear force diagram is given, and from the given shear force diagram we have to plot the loading diagram and the bending moment diagram, as well as when bending moment diagram is there, then we have to draw the loading diagram and the shear force diagram. So this two relation plays important role. So let us take one simple example on this. Draw the bending moment diagram and the loading diagram from the given shear force diagram if a beam is subjected to a moment at a distance of 2 meters from A. So this is the given shear force diagram. Given shear force diagram, here D2E, there is a constant shear force acting of magnitude 13.875. Then between C to D, constant shear force is acting in between of magnitude 3.875, and then you will get the shear force is gradually increasing, and maximum at A is 12.143 kN, and then it is 0. So now you first of all identify the type of curve. Which type of curve is occurs given in between D2E? A straight horizontal line is there. That means a point load is acting at E. Then again straight horizontal curve is there in between C to D. Again it indicates there is no point load, there is no load acting between C to D. So there is a point load acting at point D. Then they will get the straight but inclined line is there in between A to B. That means over the portion of beam AC, UDL is acting. Okay, so if a straight horizontal line is there, a point load indicates, and if inclined line is there, it indicates the UDL. And if suppose a parabolic curve is there, then it indicates the uniformly varying load. Then now we'll discuss how to draw the loading diagram first of all from given the shear force diagram. Solution. First of all, let us locate the position of the zero shear force, because at this point you will get the maximum bending moment. So by using law of triangle of similarity, here I am going to consider this distance as x and remaining is 4 minus x. So here AB is considered as x, so BC becomes 4 minus x. Okay, then using law of triangle of similarity, 12.143 divided by x is equal to 3.875 divided by 4 minus x. This equation, I have used these two triangles having height as a 12.143 and a second triangle having height as a 3.875 and base as a x and 4 minus x. Solving this equation, you will get the value of x. X means position of the zero shear force. So x becomes 3.032. So approximately it is 3 meter. Approximately it is 3 meter. from the left hand side. Then calculation of loading diagram. While you are calculating the loading diagram, so let us see if at a point there are two values of shear force that indicate the point load. So which are the points where point loads are acting? E, at E 0 and 13.875 shear force is acting. That means at E there is a point load. Then at D also you will get the two values of shear force. Also at D there is a point load is acting, but at C there is no point load. But at A you will get the two values of shear force, 12.143 and 0. So point loads are acting at A, then at D and E, and U del is in between A to C. So let us see how to calculate the point load. First of all, you take the reference line, that is a beam. Then the magnitude of a point load at E is equal to final minus initial. Final minus 13.875 minus 0 I have written here. So final value will get it as a minus 13.875. Minus sign indicate that the force is acting vertically upward, because downward is taken as a positive, upward is taken as a negative. So here you will get the force and its magnitude is 13.875. Then let us find out the magnitude of point load at D. So here again you write down final minus initial. Final is minus 3.875 minus 13.875 I have written here. So you will get the plus value. Plus value indicate that the force is acting vertically downward of magnitude 10 kilonewton. So show the 10 kilonewton force at at D of 10 kilonewton. Then there is no point load at C. Now you calculate the magnitude of UDL between point A to C, but we don't know whether this there is a straight line in between A, B, C is having slope same or not. So first of all, I'm going to calculate the magnitude of the UDL between B to C and then A to B. So the magnitude of UDL between point B to C is equal to, again you know that change in bending moment, change in shear force with respect to distance, you will get the magnitude of UDL. So here magnitude of UDL between C to B is equal to final minus initial divided by 0.968. So this distance is 0.968. 0.968. Then substitute the value of final and minus, you will get the value of plus 4 kilonewton. So the here you will get the 4 kilonewton UDL is acting between point B to C. So let us calculate the magnitude of UDL between point A to B. Again you write down final minus initial divided by a distance. Final minus initial means was change in shear force with respect to distance. You will get the magnitude of UDL. So final minus initial divided by the distance will get it as a that is 12.143 minus 0 divided by 3.032 is the x distance. So we'll get it as again 4 kilonewton. Show the UDL. That means UDL between A, B, C having same magnitude of 4 kilonewton per meter. Okay. Then lastly you find out the magnitude of the point load acting at A. Magnitude of point load acting at A is equal to final minus initial. So here we'll get final minus initial. Final is 0 minus 12.143. So final value is minus 12.143. Minus sign indicate that the load is acting, point load is acting at vertically upward. So here 12. So in this way we can easily plot the loading diagram. Once we know the loading diagram, then the remaining part becomes very simple. So from this loading diagram, we can easily plot the bending moment diagram. Before that one, whether calculated loads on the beam, these values are correct or not, or whether the shown beam is in equilibrium or not, that we want to check. That means if any bending moment is acting or couple is acting on the beam, so it doesn't show the shear force diagram. That's why we want to check sigma fx, sigma fy, and sigma m. First of all, you apply sigma fx is equal to 0. So again I have shown here or the drawn beam diagram, sigma fx is equal to 0, not a single force acting on the beam in the x direction, so sigma fx is not applicable. Sigma fy is equal to 0, so 12.143 minus 4 into 4 minus 10 plus 13.875, and you will get it as 0. That means beam is equilibrium along the x direction, beam is equilibrium along the y direction. Let us check whether the beam is subjected to any couple or not. Sigma m is equal to 0. If you are taking moment about any point, you can select moment center as a, b, c, d. So that bending moment should be 0 if the beam is free from couple. So taking moment about a, let us start from the right hand side. 13.875 into perpendicular distance is 7. Here I have written. So it will create some moment in an anti-clockwise direction. So that's why it is positive. Then moment created by this 10, it will create some moment in a clockwise direction. So it is taken as a negative. So 10 into 5.5 that I have written here. Then moment into the UDL, 4 into 4 into 2, 4 into 4 into 2. It will create some moment in a clockwise direction. So sign is negative. So you'll get the positive value 10.125 kilonewton meter. So this bending moment at edge is not equal to 0. That means the beam is subjected to couple. Now in the statement of the problem, it is mentioned that there is a couple is acting, and now we know the magnitude of the couple, that is 10.125, and it is acting 2 meter from A. So this couple, if you want to show, then you show on this diagram. Then let us calculate the bending moment ordinates. So bending moment at D is equal to 0. Bending moment at C is equal to 13.875 into 1.5. It will create anti-clockwise moment, so that's why it is positive. So you'll get it as a 20.813. Then bending moment at B is equal to, I have taken a section here, so 13.875 into 1.5 plus 1.5, it becomes 3. So 13.875 into 3, anti-clockwise positive, I have written here. Then moment is 10 kilonewton. 10 kilonewton will create a moment in a clockwise direction. So 10 into 1.5, so negative. And you'll get the bending moment at B is equal to 26.625. Then bending moment at couple, 0 shear force. Bending moment at 0 shear force, uh, you know that 0 shear force is acting 3 meter from the left hand side, correct, and 1 meter from the right hand side approximately. So 13.875 into 2 plus that 3, that becomes so here you will get bending moment at 0 shear force. So here this distance, we know that it is a 0.968. This distance is 0.968. Okay, so 0.968 plus 3, so it becomes 3.9685. So 13.875 into 3.968, it will create anti-clockwise moment. Then moment it is a 10 into 1.5 plus 0.968, it becomes 2.468, so it is minus. Again moment due to this UDL acting over this portion, over this 1 meter distance, so 4 into 0.968 divided into 0.484, this distance will get it as 0.968 divided by 2. So final value will get at a 0 shear force, 0 shear force, the bending moment is 28.502. Then bending moment at a D. Where is D? D is that point where you will get the 2 meter. So here D is this point we have considered, which is at 2 meter from the left hand side. It is mentioned in the statement of the problem. So bending moment at D, just write is this much is the forces are acting. One is 13, 10, and the UDL. That I have written 13.875 into 5 minus 10 into 3.5 minus 4 into 2 into 1. You will get the value is 26.375. Okay, then bending moment at D just left is equal to the above equation remains same. Only addition is that moment of a magnitude 10.125, and it will acting in a clockwise direction. The sign is negative. So here I have considered here 10.125. So the bending moment at D just left becomes 16.25, and the bending moment at A is 0. I shown the couple, and bending moment at A is 0. Then you try to draw the bending moment diagram. First of all, you select the reference line. So it is simply supported beam is there. So you'll get the total bending moment is positive. So bending moment at D is 0. Bending moment at C is equal to plus 20.815. So 20.813, a straight line because it is a point load. Then bending moment at B is equal to plus 26.25. Again straight line because there is no U del is acting between B to C, or uniformly varying load is acting in between B to C. That's why it will be a straight line. Then bending moment at 0 shear force, you'll get this value as plus 28.502. Then bending moment at D just right, you'll get this value as a 26.375, and bending moment at D just left is plus 16.25. So we'll get the parabolic curve between D to B, then suddenly drop in bending moment at point D because there is a couple, and again parabolic curve is there between E to D. So in this way we can easily plot the shear force, loading diagram and bending moment diagram from the given uh, shear force diagram. Another one example, uh, how to draw the loading diagram and the bending moment diagram. So this problem we will be going to discuss in the next video lecture. So this is the loading diagram. You take this example as for the practice. It's a bending moment diagram. Thank you.